Hello everyone, and welcome to our presentation. Today we're going to introduce to you our work, SpeedyRecs, which is a recommender system for anime content. We have been developing SpeedyRecs throughout the summer semester for our data mining course. Presenters for today are Mark Cunningham, Brandon Stickney, and myself, Ethan Saloom. We're excited to show you what went into this and the results taken from it. Before we get started, let's take a little look at what will be discussed today. First, we'd like you to become a little more familiar with this area by giving an overview and our introduction. Next, we'll go over related works to our project and some background on why we felt there was a need to develop SpeedyRecs. We'll then get into our proposed work and results, going more in depth on the data pre-processing procedures, the algorithms we used with our data, and how we evaluated our model. Along with the conclusions we arrived on, we'll also express where future work can put focus towards, and then we'll actually show you a demo of SpeedyRecs. So, recommender systems. They are machine learning systems aimed at predicting the rating or preference of a user to further suggest relevant items. Currently, very few recommendation systems provide recommendations for anime, nor allow users to explore the different ratings based on each algorithm. Therefore, our objective was to develop a system that recommends new anime for users to watch based on the anime titles they previously rated. In addition, a system that supplies the availability of viewing ratings based on certain algorithms. For this work's purposes, anime refers to all categories or formats that MyAnimeList separates Japanese animated content into. We will use 5 algorithms to compute ratings by users and recommendations for users, which we will go into further later on. We use the program RStudio to manipulate our data, create models, and generate recommendations. This allows us to analyze algorithms for error and compare how each algorithm performed against one another. We were able to generate faster recommendations by narrowing our search, and once a recommendation was produced, we then calculated error between the test and the generated value. Plotting errors for each algorithm, we were able to visualize which one was generating better recommendations. For related works, MyAnimeList provides basic suggestions relying only on viewing one anime title, but it is not based on a combination of viewer rating history, which is what we intend for SpeedyRecs. Siobhan Biswas's work compared algorithms, but it did not adjust parameters and offered no application. Taras Knott compared some algorithms and even adjusted algorithm parameters, but he did not use anime. Along with many recommenders, not including anime recommendations, our takeaway was that many recommenders do not provide an in-depth description behind parameter settings, algorithm differences, or the application to view the outputs of differing algorithms from user input. Moving on to our own work, here is the layout of the procedures we took in developing SpeedyRecs. First, dealing with the data, and then we move towards implementing algorithms on the data. We then diligently evaluate our model and build the application to be used. Our dataset came from the Anime Recommendation Database, which retrieved data from MyAnimeList. The database had numerous spreadsheets, but we only wanted to use the anime and complete ratings datasets. Explicit content was filtered out, as well as anime that had less than 1,000 users who watched it completely. Users with less than 100 ratings were also filtered out. That's because users with very low amount of ratings can slow down the efficiency of algorithms that depend on user item matrices. The ratings data frame was updated, and columns from anime data frame were actually removed if we did not intend to use them. Below is an updated view of our dataset after filtering. The anime data frame consists of 18 attributes such as genre, rating, ranking, and popularity. The ratings data frame included an anonymous ID for each user and their rating for a given anime. Looking at the types of anime included TV series make up a substantial portion of anime. To ensure that our algorithm's comparison would be unbiased, the ratings data frame was sampled. We initially converted the data frame into a real rating matrix to serve as inputs for our algorithms, but still the matrix was too large to be processed. In response, we then sampled real rating matrix using a sample function in program R. Setting a value of 1,000 anime, random sampling generated relatively quick recommendations. The result of the new sample was approximately 260,700 ratings with 5,000 users randomly sampled. After filtering and sampling, we see which ratings are most common, and that is a rating of 8. Normalizing the ratings, we see that the ratings are normally distributed with a concentration towards the center of the distribution.
Hello, My name is Branson Stickney, and I'm going to pick up on the post-sampling data preview. Here we have a normalized graph of our users with greater than 100 ratings. As we can see, most of the users are concentrated towards the 100 to 300 rating range, with a steep drop-off afterwards. Next, we can start examining the similarities between the users and the items. Here, we use the distance measurement of cosine similarity to find the distance between each of the items and the users. And then we graph them on a non-normalized and a normalized graph. Now, let's examine the similarity between individual anime and the similarity between individual users. We see that the anime similarity have lighter colors than the user similarity does. This signals to us that the anime have less in common than the users do. The anime similarity image has greater deviations in color than the user one, which suggests that there are higher levels of differentiation between individual anime. Of course, this is only for the first 100 items, so it might not paint the full picture for the full dataset. For SpeedyRecs, we utilized user-based collaborative filtering, item-based collaborative filtering, and matrix factorization with the combination of alternating least squares. Collaborative filtering is a widely used approach to create recommender systems that uses the assumption that if two users have similar ratings for a particular anime, they are more likely to have similar ratings for another anime than a randomly selected user. It relies on user ratings to generate a list of similar users, or to generate similar anime. Collaborative filtering consists of memory-based and model-based techniques. Latent factor models are another popular choice in recommender systems. They use matrix factorization to uncover latent features that explain observed ratings. Recommender Lab offers the evaluation scheme function, which allows the user to specify how the train and test sets should be divided and how they should be evaluated. We created 4 evaluation scheme objects in our R program, 2 split methods and 2 cross methods. In the split method, users are split into 2 groups. The first half of the split is to train the model, which is 80% of the data set. The second half of the split is to evaluate the model, which is the latter 20% of the data set. If using the all but X given scheme, the second half of the split is only used to exclude ratings from. For our cross methods, we used k-fold cross-validation and the user specified k-value as the number of folds. For both methods, the given parameter values we set to the minimum number of rating in the data frame. All but X approach was used with X equals 5. Next, let's talk about item-based collaborative filtering. It is a model-based technique and generates its recommendations based on the similarities between items learned from an anime-anime matrix. We use the cosine similarity method to measure the distance between the ratings. The ratings are normalized using a parameter argument within the function call. This algorithm can be broken down into 3 steps. First, all similarities between anime are stored in a matrix. This is the learned model. Second, a given user inputs the ratings for a number of anime. Lastly, the weighted sum of the user's ratings is calculated from the similarities and the ratings for anime that the user has seen. The result is a list of anime with predicted ratings. The value of K in the item-based collaborative filtering model corresponds to the number of closest neighbors to store for each anime. We measured the values with 10 different K values using the predict function available in base R and the calc prediction accuracy function from Recommender Lab. The results are shown below. The error curves appear roughly mound-shaped, indicating that the lowest and highest K values have the lowest errors. However, we didn't want to use a low K value since that wouldn't allow a large number of similar items, which might be necessary because our program only takes in 5 ratings from the user. We ended up choosing K equals 50 as we noticed a decline in the error. Next is user-based collaborative filtering. It is a memory-based technique that finds unknown ratings for a user by finding a neighborhood consisting of K most similar users. We again used the cosine similarity to measure the distance between the user points. User-based collaborative filtering can be broken down into 2 steps for a given user seeking recommendations. 1. The K most similar users are found based on their user anime similarity. And 2. It generates an average rating for each anime not yet rated by the given user based on the averages of the users within the neighborhood consisting of K most similar users. As explained earlier, using the cosine similarity to measure the parameter for our model, we then selected the highest rated anime from the list of averages within the neighborhood. The figure below shows visually how the algorithm works. Our next decision in user-based collaborative filtering is which NN value to choose. The value of NN represents the number of nearest neighbors the algorithm calculates for each user. The error values for each NN value are shown with 10 different NN values. As we can see, around NN value 50, we start to reach diminishing returns. So once again, we choose 50 since it is appropriate trade-off between prediction time and error rate. Finally, I'll talk about alternating least squares. Singular value decomposition will be used towards dimensionality reduction by breaking down a higher level matrix into lower order matrices, which is done by transforming correlated variables into a set of uncorrelated ones. However, matrix factorization is only a pre-processing step, so the matrix still needs to be solved. Alternating least squares helps accomplish this by minimizing the error between the predicted and true values of the SVD matrix. It works by solving the k-dimensional vectors xu, which is every user, and y sub I, which is every anime. Within Recommender Lab, 2 parameters pass to the model creation function, in factors and in iterations. In factors are the number of latent factors the model creates based on the lower dimensional matrices. For SpeedyRex, we left in factors value as the default, which is equal to 10. In iterations is the number of iterations that the model undergoes when solving for the unknown ratings. Once again, for SpeedyRex, we lowered the in iterations from 10 down to 5 in an effort to increase the speed of recommendations.
Hi, my name is Mark Cunningham, and I'll begin by talking about one of our algorithms, singular value decomposition. Singular value decomposition is accomplished using column mean imputation, which replaces the NA values with column means and further simplifies the matrix until convergence. The solved matrix has ratings for every entry inside the matrix and it has a unique solution obtained after the convergence. A hybrid model is a simple weighted combination. Individual ratings from each algorithm included within the hybrid model are combined using a weighted sum. So for our case, these 4 rating matrices are combined into one by summing all the ratings after applying their weights. In order to evaluate our models, we use the main method of error measurement to evaluate. In this, there are 3 rating accuracy methods, which include root mean square error, mean squared error, and mean absolute error. In order to use these, the data is required to be split into training and test sets, and also evaluation schemes. The first step is to retrieve the error measurements is to calculate the predicted ratings for the known portion of the data. I think it's easier to explain this using an example because there's a lot of known given things going on. But for example, if we use an evaluation scheme with an 80%, 20% split and an all but 5 given parameter, 80% of the users will be used to train the model, while the remaining 20% will be used for evaluation. Within this 20%, all but 5 ratings for every user are given to the trained model, and the model predicts these 5 ratings for every user. The result is a matrix containing 20% of the users with those 5 new predicted ratings for each user. The getData function from Recommender Lab is used to retrieve the known partition of the evaluation scheme, along with the predict function. Next, we take a look at actually calculating the prediction errors of the algorithm's ratings. These are the ratings that are compared to the actual ratings that were withheld from the model in the previous step. We use calc prediction accuracy from Recommender Lab to return these error values as shown in the code snippet. Once again, the getData function is used, but this time it retrieves the unknown partition of the evaluation scheme. The algorithms with the lowest total average error were the alternating least squares algorithm and the singular value decomposition algorithm. This means they predicted the closest to the withheld ratings. However, error level doesn't directly correlate with rating accuracy in the grand scheme of things, but it shows how well the algorithms are able to predict ratings based on trained data. Next, we look at the effect of using different values for the given parameter within the evaluation scheme. The all but 5 method returns a lower error value because they are able to intake a greater number of ratings before the models have to predict the remaining ones. Using the given parameter equal to the minimum number of user ratings in the data frame, which in our case is 100, results in a slightly higher error, but not by much. Next, we take a look at the split versus cross method, which is using an 80-20 split versus using 4-fold cross evaluation. Both methods turned out to be quite similar when measuring the error rate. This suggests that both methods are suitable for evaluation, so we chose the split method since it evaluates quicker. The precision recall curve gives information about how often the recommenders give correct or incorrect recommendations when we implement a pass-fail rating. Here we implemented one of 5 out of 10. The graph shows precision and recall plotted against each other and how the algorithms perform when returning a top-in list of predictions. We used values of 1, 3, 5, 10, 15, and 20. From the graph, we could see that item-based collaborative filtering and alternating least squares are the top performers, but level off once the size of the list increases. The smaller the slope means worse predictions, so user-based collaborative filtering is the worst performer here. The ROC curve plots the sensitivity against the specificity using true and false positive rates. Here, a random classifier has a slope of 1, but the x values in our graph are shrunk, so it actually appears to be a slope of 0. All of our models outperformed the random classifier, which is great, but user-based collaborative filtering is once again the worst performer, with item-based collaborative filtering, alternating least squares, and singular value decomposition clearly ahead of it. More often than not, anime that are very popular are also highly rated, so it makes sense that the popular algorithm also performed very well. Next, we take a look at how we built the application. We built it using Shiny from our studio, using our studio. There are two main components of a Shiny application, the UI and the server. The UI is the front end of the application, and it displays components and renders them to the user. The server is the back end of the application, and it updates the UI based on user input. It uses the user input from the UI features and feeds it to the algorithms, and then the algorithms feed the output back to the UI. Here we can see screenshots of the application running on my computer. The next slide shows the outputted recommendations for all four algorithms. In conclusion, we realized that strong recommendations require large data sets, but many of the data sets we encountered included a large amount of data that weren't relevant to our goals, so we had to implement time-consuming data pre-processing techniques to get the data where we wanted it. The Recommender Lab package was great to work with, but it still took time to thoroughly understand all the functions and all the parameters that we should pass through them. The algorithms and prediction models had their limits, but we found that most performed quickly and had a low value of error, apart from alternating least squares, which unfortunately was extremely time consuming, and we just couldn't make it any quicker without sacrificing recommendation quality. We're also happy to see that our individual recommendations that we found using the application were relevant and appropriate to our tastes. For future work, we have a few suggestions. We would have liked to add a popular option in the application which only recommends anime based on a certain level of popularity criteria, either by implementing popularity ranks that are already found within our data frame or by using the popular algorithm within Recommender Lab. Updating the data to the current year by rescraping from my anime list would be a great step in making this project even more relevant. We could also set up a data scraping system so that the system automatically grabs data at set time intervals. We're also working on publishing the application to shinyapps.io so our friends can also use it. However, we encountered a memory usage problem and are going to have to slim it down or buy the premium version. Thank you for listening to our project report.
I will now begin the demonstration of our application. So this loads up in a separate window. I'm going to make it bigger and select some anime. As you can see, the list updates as I type, and it does that every time I type a letter. So now that all the forms are filled out, we can click a button to start getting some recommendations. And it shows the output right over here. And let's do it for all methods. And the ALS method is actually going to take 20 to 30 seconds, I believe. just because we couldn't get the algorithm to do it any quicker without compromising recommendation accuracy. So I'll briefly describe how the app is set up. There's this UI section and then the server section, and as previously described, the UI basically displays all these components that you see here, and the server is updating the choices in the boxes as well as feeding the information from the boxes to the functions, which are located in the user recommender file. And this is just an extension of the app.r file. And it just sources that file. It just reads from it and copies it into this file. And this is where all of the algorithms live. So back to the program, we see that the ALS method has generated our recommendations, and let's also get the last two. SVD, and then hybrid also takes a little bit because it's redoing all 5 models that it is comprised of, mainly because with user-based collaborative filtering, it's actually building a new model each time it takes an input in, unlike item-based. Item-based, it just generates the model and that's it. It doesn't matter what the user puts in because it's still going to return based on just item similarity instead of user similarity. So let's go back to item base and start changing some values and see how sensitive it is. Oh, that got a lot of change. And so did that. So it's most sensitive on the higher end of the spectrum, and it seems to not mind if you rate it pretty low. But these are also tied together since there's season 1 and season 2 of a given anime. Okay, let's go to user-based. And these are also pretty sensitive to change. Okay, so we see that we're getting recommended Naruto. What happens if we change that value? And this error is only occurring because it's constantly updating, and it's actually feeding an empty box, which is breaking the program, but it won't exit us out. We just have to type in a new one and it'll start working again. Let's rate this a 1. Oh, yep. See that we no longer are getting recommended Naruto. And that should be what's happening. But what if we put it to a 10? We do get recommended Naruto once again. It seems even if you rated a 9, you will not get recommended it. Interesting. And that concludes our anime recommendation system for our project. Thank you.